Hello there and welcome back to our module on probabilities, and we're going to be looking at dependent and independent events. We'll be returning to look at the total probability rule, and we'll start to look at expected values. So our first learning outcome statement here asks us to compare and contrast between dependent and independent events. Let's start with independent events. Knowing the outcome of one does not tell you anything about the probability of occurrence of the other. In other words, the event's occurrence has no influence on the occurrence of other future events. Okay, so think about this like a toss of a coin. Let's say you toss a coin and you get heads, and then you're asked what is the probability on a second toss of getting heads again. Well, of course, it's still 50. Okay, you've got a 50% chance of heads, 50% chance of tails. It is not affected by the fact that you previously tossed the coin and got a head in the previous toss. So, coin tosses, dice rolls as well. So you've rolled the dice once and let's say you get a 4, and we want to know what is the probability of getting a 4 on your next roll. Well, the fact that you got a 4 on your previous roll does not affect the probability of getting a 4 on your next roll. It's still 1 in 6. So we talk about those as being independent events. And notice when we do this, we say the conditional probability of event A occurring given that B has occurred is simply equal to the probability of event A occurring. In other words, event A is not influenced in any way, shape or form of whether event B occurs or not. Now let's contrast that with dependent events. With a dependent event, knowing the outcome of one tells you something about the probability of the other. In other words, an event's occurrence does impact the occurrence of future events. Let's think about lottery balls here. Now, the probability of a ball being chosen is going to change with each pick as the number of remaining balls are reduced. So, for example, let's imagine we're looking at the first pick and we want to know what is the probability of picking a 12, and there's 50 balls in our lottery. Okay, so the probability of picking a 12 is 1/50th. Now, let's imagine the second pick. Let's assume that 12 was not selected in the first pick and go on to the second pick. Now, what is the probability of picking 12? Well, there's only 49 balls left, so it's 1 in 49. Okay, so with a dependent event, the probability is changing based on the outcomes of past events. So our conditional probability, the probability of event A occurring given that B has occurred, is not equal to simply the probability of event A occurring. Okay, so let's return to our total probability rule here. Now, the LOS asks us to calculate and interpret unconditional probabilities using the total probability rule. Okay, so look, we're looking for the unconditional probability of event A occurring here. So the unconditional probability of event A occurring, and we've been given some conditional probabilities and unconditional. Of course, if you take a conditional probability and multiply it by an unconditional probability, you've got a joint probability. So the unconditional probability for event A occurring is simply all of the joint probabilities where A occurs. Now notice with our unconditional event here, we're calling it S, S1, S2, Sn, okay? If we take our unconditional probabilities and sum them, they have got to come to 1. Okay, let's have a look at an example with our total probability rule. And we did this, covered this in the previous module. We're looking at interest rates increases. We've got an unconditional probability of an interest rate increase of 40%. So no interest rate increase, probability 60%. We've then been given a conditional probability of a recession given an interest rate increase of 70%. And also the conditional probability of a recession given no interest rate increase of 10%. And we're asked overall, what is the unconditional probability of recession? So we're going to be using the total probability rule, but again, I think doing them via decision trees or diagrams is the easiest way to go. So let's have a look. We've got, get a pen up, would help. Okay, so we've got a 40% chance of interest rates increasing and a 60% chance of interest rates not increasing. Okay, so those are our unconditional probabilities, and they will always come first in our probability tree. We've then told that if interest rates increase, there is a 70% chance of a recession. So we've now got our conditional probability. 70% chance of a recession given interest rates rise. Now that must be, therefore, equal to a 30% chance of no recession. Remember, our probabilities at each node in the tree have to add up to 1. So, no recession. We're also told in this example that we've got a 10% chance of a recession given no interest rate increase. So again, we can put on recession and no recession. So we've got a 10% chance, 0.1% chance of witnessing a recession given that we haven't seen an interest rate rise, and a 90% chance of no recession given that we haven't seen an interest rate rise. Now, we are interested in the unconditional probability of a recession. So there are two scenarios. You could have an interest rate rise and then a recession, or you could not have an interest rate rise and then a recession. So what we want to look at is the joint probabilities of these two events occurring at the same time. So an interest rate rise and a recession, well, that's going to be 0.4 times 0.7. So that gives us a joint probability of 0.28. So there's a 28% chance that you'll see an interest rate increase and a recession. We also need to analyse no interest rate increase and a recession. So that's 0.6 times 0.1, which gives us 0.06. So there is a 6% chance that you will see no interest rate rise and a recession. So what is the unconditional probability of a recession? Well, 28% chance of recession and interest rate increase, 6% chance of recession and no interest rate increase. Add these two together and we've got our outcome of 0.34%. So there's a 34% chance that we will see a recession, and that is the independent unconditional probability, therefore, of a recession. Now, we could finish our decision tree off as well. Look, there's a 40% chance of an interest rate increase and a 30% chance of no recession. So no recession given an interest rate increase, that's going to come out at 0.12. And 60% chance of no interest rate increase and 90% chance of no recession. So the joint probability of no recession and no interest rate increase is 0.54. Now, of course, if we take these two probabilities, we're getting the unconditional probability of not seeing a recession. Well, if the unconditional probability of witnessing a recession is 34%, then we should see that this comes out at 66%. 0.54 plus 0.12 is indeed 0.66. Now notice if you take all of your joint probabilities, okay, so this one, this one, this one, and this one, and add them together, you will come to 1, okay, because we've got all of the potential outcomes. But here we were asked to calculate the unconditional probability of witnessing a recession, and it is 34%. Okay, and that is using the total probability rule. I find it easier to do it via a decision tree like this, a probability tree like this. I think it becomes very, very obvious at what you're looking at. Okay, so what is the unconditional probability of recession? Well, it is the probability of a recession given an interest rate increase times the probability of an interest rate increase. We saw that. That was our joint probability when we got 0.28 on our decision tree. And it's the probability of a recession given no interest rate increase times the probability of no interest rate increase. And of course, that was our 0.06 or 6%. add the two together, and we've got our 34%. So you certainly don't need to do it with decision trees, probability trees. However, I tend to find that it makes it obvious what I'm looking at, makes the answer more obvious. And certainly whilst you're picking up probabilities, I would certainly recommend sketching them out and labeling them. Okay, so our next LOS. Our next LOS is looking at calculating and interpreting expected values and as well standard deviations and variances. Okay, so we've got to calculate and interpret expected value, variance and standard deviation. Okay, we've got a little example here, probability weighted average of all possible outcomes, and we've got an example, earnings per share for Ron's Stores, where we've got a 10% chance of £1.80, I should say, 20% probability of an EPS of £1.60, 40% probability of an EPS of £1.20, and finally 30% probability of an EPS of $1. Now all we need to do is take the probability, multiply by the outcome, so 10% of 180, plus 20% of 160, plus 40% of 120, plus 30% of £1, add them together and we get our results. This can be done on the BA2 Plus calculator. So I'm just going to bring my BA2 Plus calculator up for a second. There we go. Now to do this, you'll want yourself in data entry mode. Second function number 7, okay, and it's asking you for your X variable. Now the X variable in this case will be our earnings per share. You might need to strip data out of your calculator before you do this if you've done previous computations. In the data mode, just do second function, clear equals cancel to strip out any data. So I'm going to type my first X variable, which is £1.80, and then press the enter key. I then press down to get Y01 up. Now Y01 is going to be the probability of my X variable occurring. So I need to tell my calculator 10%. Just be aware that when you enter probabilities on your calculator, you enter them as whole numbers and not as decimals. So we're going to enter 10, not 0.1. Okay, press the down arrow, X02, my second variable, which is £1.60. In it goes, enter, down arrow, its probability 20%. So we type in again 20 and press enter. Down again, X03, 120, and the enter key. Down for our probability, 40%, so 40, and enter. Down one more time, X04, that's £1, £1, enter, and its probability 30%, so 30, and enter. Okay, it's only the probabilities that have to be entered as whole numbers, rather than decimals. Now, I'm then going to go into stats mode, second function, and number 8. Now, I don't want linear regression. Lin stands for linear regression. If I do that, my calculator will interpret the Y data I've entered in the calculator as a second variable, and it will attempt to regress the X and Y variables together. Now, my Y data is not a second variable. It's the probability of my variable occurring. So I need to change my calculator mode, and I'm just going to press second and enter. And I'm going to keep on doing second, enter, until I see 1 minus V on my screen. Now, 1 minus V means one variable. So I'm telling my calculator I've only got one variable here, the X variable, and therefore your calculator will interpret the Y data you entered in as probabilities. Now I can press the down arrow once. It tells me N equals 100. So I've got 100% of observations. In other words, my probabilities add up to 100 or 1 if you like. Press down again and there you go. You have got your X bar, your arithmetic mean of this data. Okay, and it's 128. Okay, let's turn our attention to our next slide. And it asks us to calculate the variance and standard deviation for Ron's Stores. Now we've actually already got the information in our calculator to compute this. But we're going to do it old-fashioned way, first of all. So notice what we're doing is we're taking each variable, comparing it to the mean, squaring it, and then multiplying by its probability. And then we're going to sum that for all observations. So the first outcome was an EPS of 180. So 180 minus 128, square the difference and multiply that by the probability of that outcome occurring, which is 10%. The next potential variable was 160, an EPS of 160. So 160 minus 128, square the difference and then multiply by your probability of that EPS occurring, which is 20% or 0.2. Do this for all of your outcomes, sum them up, and you've got the variance of 0.0736. And of course, if we square root our variance, we get our standard deviation, 0.2713. Okay, now, as I said, you can do this on the calculator. Let me get my calculator back on my screen. Okay, so here it is where we left it. Now notice if I press the down arrow one more time, I get SX. And SX is the sample standard deviation. Now, we were using sample standard deviation in our earlier module because we were looking at the standard deviation of a sample of historic data and using it to predict the population standard deviation. But here, we're not doing this. This isn't historic information. This is forecasts. And note, our probabilities add up to 1. 10%, 20%, 40%, 30%. It adds up to 1, or 100% of outcomes. So because we're dealing with 100% of all potential outcomes, we're dealing with the population of outcomes, not sample data. So we use population standard deviation. Press down on your calculator one more time. There you go, sigma x, that is population standard deviation. So if you remember for your exam, if you've got a historic sample of data, then typically we use sample standard deviation. If we've got probabilities involved that sum to 1, then we use population standard deviation. And you can see there's our answer of 0.2713. Now, of course, your calculator doesn't calculate variance, it calculates standard deviation. Well, of course, I can get to variance simply by squaring my standard deviation, and there's the variance, 0.0736. Lovely. Okay, so let the calculator take some of your pain in terms of doing these computations. Now, let's have a look at our next LOS. It says, explain the use of conditional expectations in investment applications. So what have we got here? We've got the probability of a tariff being enacted, 40% chance that a tariff will be introduced, and 60% chance that a tariff won't be introduced. What we've then got is contingent expected returns. Okay, now notice it's not a probability because it has E here, so it's an expectation, and it's the expected return given that a tariff is introduced, and that's 15%. The expected return given no tariff is introduced is 5%. So we can work out the unconditional expected return just using our total probability rule as before. So 40% of 15 plus 60% of 5, and that gives us 9%, the unconditional expected return. Okay, and we've got an investment tree, and it now asks us to interpret a probability tree and demonstrate its application to investment problems. Now we've got an unconditional event, and we always start with our unconditional event, and that looks at GDP growth being greater than 3% or being less than or equal to 3%. And we're told there's a 60% chance that GDP growth will be greater than 3% and a 40% chance that it will be less than or equal to 3%. We've then got our conditional probabilities. So there is a 30% chance of an EPS of 180 contingent on GDP growth being greater than 3%. So in other words, the probability of EPS of 180, given that GDP growth is above 3%, is 30%. Okay, now, what is therefore the probability of having both GDP growth above 3% and an EPS of 180? Well, it's going to be 60 times 30, which is going to give us a joint probability of 18%. So we're going to say there is an 18% chance that you will receive an EPS of 180. Okay, now let's have a look at the second scenario. This is an EPS of 170. And we're going to say there is a 70% chance of receiving an earnings per share of $1.70 given that GDP growth is above 3%. So the chance of EPS of 170 and GDP growth above 3%, 60 times 70, and that's going to give us 42%. Okay, so now let's turn to our attention to the unconditional event of GDP growth less than or equal to 3%. 40% chance of that occurring. Now we're told if GDP growth is less than or equal to 3%, there is a 60% chance of an EPS of 130. So the probability of GDP growth being less than or equal to 3% and an EPS of 130, 40 times 60, and that gives us our probability of 24%. Final one, we're looking at EPS being $1 given that GDP growth is less than 3%, so 40 times 40, and that's going to be 16%. And as per normal, notice with your joint probabilities, if you sum them, they sum to 1. Our probabilities always sum to 1. The unconditional probabilities, 60 and 40, sum to 1. The conditional probabilities, given that GDP growth is above 3%, sums to 1 or 100%. The conditional probabilities given GDP growth is less than or equal to 3%, sums to 1. And our joint probabilities here, 18 plus 42, that's 60, plus 24 is 84, plus 16, it also adds up to 1. Now, we're going to use this investment tree to get an unconditional expected return on our stock. And all we're going to do, therefore, is multiply 180 by 18%, 170 by 42%, 130 by 24%, and $1 by 16%, and then we're going to sum all of these observations. Okay, so let's do that. So I'll get my calculator out. So 0.18 times 180, so that's 0.324, plus 0.42 times 170, which is 0.714. Add them together, you're now looking at 1.038, plus 0.24 times 130, which is 1.35. Oh, no, I've made a mistake on my calculator now. Oh, no, 1.35. And then 16% of 1. Add them together and you get 151. Okay, so very nice and straightforward and easy to do. And that is the unconditional expected return on this stock.